We will discuss more on Stone-Weistrass theorem. In the last class, Bhanukiran proved Stone-Weistrass theorem for a compact metric space. I will recall that. We will discuss slightly more on that, and then we will discuss Stone-Weistrass theorem for a locally compact metric space. Okay. There is something on topology which I will not do because I think it will be done. I wanted to. I mean, the CMI was not accessible from my home, so I didn't check the syllabus for topology next semester. I think there is some Urison metrization theorem or something is there. It's in the next semester. Okay. You know already. Okay. So you already you have not done it. Okay. No, Urison metrization theorem that any separable metric space, any separable topological space, and second countable topological space can be embedded in Hilbert cube. Okay. Hilbert cube. Hilbert cube is something I have given it as an assignment, which is just 0, 1. You take the infinite, countably infinite product, and then define a topology using that sum. It will be exactly point-wise convergence will be equal. Convergence there in the infinitely many coordinates. A sequence will be point-wise convergence. It was in the assignment. Yeah, exactly. The direct product of countably infinite direct product. Any second countable topological space. Hausdorff, I think. Yeah, Hausdorff. Yeah. In particular, locally compact and separable can be embedded. I am not very comfortable with general topological space. Okay. I mean, I deal with that, but very little. Normal is needed. I'm not sure. I will check and tell you. I don't remember. I'll check it and tell you.
Normal spaces in Hausdorff.
No, normal. I mean, Hausdorff means you can.
Spaces are normal.
No. Here he's talking about general topological space. I mean, this is just to tell you. I will talk about some one-point compactification of a locally compact space, metric space, and whether it is metrizable is not clear. I will provide a topology. Okay, it is metrizable. Will follow from that theorem. That's what all I want to say. I don't want to go through that. That will I need to spend one class on that, which I don't want to do. So that's the only thing I'm going to use. Okay. Okay. So this is the definition. Recording. It's recording. So a metric space, of course, we deal with metric space. X is said to be locally compact if every point, if for all x in X, there exists a compact neighborhood. That is, there exists a U which contains X such that U closure is compact. Okay. U is open, of course. Okay. Or there exists a K whose interior is, I mean, then you have to say that X is in the interior. So there exists a compact neighborhood. There is a compact set containing this. Okay. So this is what is locally compact. There is a compact neighborhood around every point. So it's locally compact. That's what locally compact. Locally means there is always a neighborhood. Locally Euclidean, everything. Locally means there is a neighborhood around that, open set around that where it is true. Okay. So example, of course, all compact sets are true, of course. I don't need to say. The Rn, Cn, of course, all those things, and any finite dimensional non-linear space. Okay. Any finite dimensional non-linear space. We know that all open balls are compact there. I mean, closure of the open balls are compact. Okay. Open balls are totally bounded. So it's if and only if I have vector space, non-linear space is locally compact, if and only if it's finite dimensional. Or you can take any open subset of a compact metric space. Okay. Of a compact metric space. If you take an open subset, you take any point, I mean, you restrict the metric to that open set. If you take any point, then there is an open ball around that which is contained in that, and that closure will be compact because the whole set is compact. So that is everything. So in fact, every locally compact will actually look like that. So you can have, if you have a locally compact subspace, you can actually embed it in a compact metric space. I mean, metric space. We will talk about if it is separable actually. I mean, we need separability for that. So such that it's open there. It sits as an open dense subset. So these are the examples. Then there is this one-point compactification. There are other compactification. Compactification means you have this, you have a X is a locally, X is a metric space. It's a locally compact metric space. There is a K somewhere else where X is embedded into K continuously as an open dense subset, where and then that set is compact. But the bigger set is compact. That's what compactification is. This is one-point compactification is a standard way of compactify so that we can deal with that. For example, we can prove Stone-Weistrass theorem using that. Okay. Okay. So there are other compactification. I think you will see in the topology course the next semester. Okay. So what we do? So X is locally compact. So it's a metric space, and it does all the open sets. Okay. And you take some point, infinity be some point. Okay, you can take x naught, you can take anything you want. I call it infinity. Infinity is just a point. I call it infinity. Okay, infinity is just a single point. Okay, so let x bar equal to x union this infinity. Just I'm adding one point to that. That's why it's called one-point compactification. Okay. Okay. Then define U contain, define open sets. I have a locally compact metric space. I have added one point to that so that it becomes this is x bar, which is the superset. And then I want to define open sets on this. I have to declare what are all the open sets. Okay, a set U containing in x bar is open. Is open for, we define it in the following way, is open. I have to say U contained in X, then X is open. Sorry, and then U is open in X. Okay. If you, let me say, is open for U such that infinity is not in U, okay, then is open if and only if U contained in X is open. Okay. There is a definition of open sets in X. Okay. If infinity is not there, then it has to be in X. So it has to be open. That's all. Okay. If infinity is in U, okay, then U is open. If, this is definition. And just definition. If U complement contained in X is compact. Okay. Of course, it is locally compact, so there is a lot of compact sets. So infinity is just something. You call it anything. Orange or apple. I'm just calling it infinity. Because for real line, you can add the infinity to that and do that. To complex plane, you can do complex plane is like this. You take one infinity and do like this, it will become a sphere. Okay. You add one point and then do everything, it will become a sphere. If you have a real line, you add one point and that will become the circle in R2, topologically. Eh? Why is? U complement is? Yeah. U complement is compact. It's not closed, it's compact. Why? If it is locally compact, it's not compact. X is not compact. X is compact, you don't need to compactify, it's already compact. Just I'm adding one single point. There is no topology in the X bar. There is no metric in the X bar to start with. But there is nothing like isometry or anything. It is just a set. I'm just adding one point to that. Okay. Okay. So, I mean, or we can say the following: let tau contained in power set of X be all open sets in X. Okay, then tau tilde equal to tau union all those U such that infinity is in U and U complement contained in X is compact. Okay, this is a collection of sets. Okay, I taken all open sets in X. Further, I add all those sets such that, I mean, such all compact sets here such that the you come in I mean, all those with infinity such that its complement is compact. Okay, so then this X bar tau tilde is a topological space, or I mean, or we can say it the other way. Then tau tilde is a topology on X bar. Okay, it is easy to verify. First, what do you have to do to say something is a topology? I will orally say it. It's an exercise. Okay, but I will tell you the proof. Okay, first, empty set has to be there. For that, X bar has to be there. X bar contains infinity, so its complement has to be compact, which is empty set, which is compact, of course. Whole set is there because already that is there. So then, if you have some arbitrary union of sets here, so if that doesn't contain any infinity, none of the sets contain infinity, then there is no problem. Then the union is again going to be some open set in X. Okay, if it contains infinity, one set is going to contain infinity. Okay, its complement is compact. If we take the complement of whole union, that will be contained. I mean, that will be contained in there. So that will also be compact, which is closed and contained in some compact set. So that is compact. Okay, so that's also open. Okay, so and then arbitrary and finite intersection. If you want to see finite intersection of these things, again, if the problem arises only when infinity is there. Okay, huh? Yeah, infinity is there. I mean, no, infinity may not be in all of them. If it is in one of them, it will be in the intersection. All of them means what? Say it again. What is the problem? Why it has to be in all of them? I don't understand. What are you asking? What is the question? I don't understand. No, we are verifying it's a topology. For that, arbitrary union has to be there, finite intersection has to be there. Arbitrary union you can verify. Finite intersection, the same thing. What is infinity? Suppose infinity in one of those, infinity is not in all of the set, then there's no problem. Infinity is in one of the set, then it will be in the intersection. Why it has to be in all of them? Yeah, infinity can be in all of them. If one of them is, I mean, if it is in at least one of them, the same as in all of them also. I mean, it can be in two of them, it can be in three of them, doesn't matter. Huh? What is that to fix? You have some un, okay, ui, I equal to 1 to n. You want to verify that this is a open set. Okay, Vex is in one of those, infinity is in one of those ei. Okay, then you want to verify that. Yeah, so then you want to see that it's all the close. I mean, the complement is closed in the topology. Okay, and that is going to be infinity in. So it is just the union of all those ui complement, and they are all.
Either infinity is in one of them.
Okay.
In which case, you have to do what you're saying. But if infinity is not there in one of them, then in the whole intersection, infinity is not there. So you have to show that thing is in the topology term.
Yeah. Yeah. That. Yeah, if it is in one of them.
Then you have to take the intersection.
Yeah. Okay. No, is there a problem or is there not a problem? Okay, you verify it. Okay, it's something very simple. I don't understand the problem, but it should be very easy. Okay, it is just a standard thing. Okay, this is an exercise.
For all of these definitions, we don't actually need locally compact, right? As long as it's just a metric space.
Yeah, whether you have enough compact sets, it's not clear. No? Okay, fine. Yeah, fine. Yeah, but we want to show that we want to show that that is compact. I mean, the point is, proposition is X bar with this tau is compact. Compact as a topological space, not as a metric space. Okay. So every open cover will have a finite subcover, in the sense every open cover will have a finite subcover. But this is also very easy. If you have an open cover, okay, let's say proof. If union of alpha u alpha is equal to X bar, okay, then infinity has to be in one of them. Okay. Yeah. Okay. I mean, you take all the sets. I mean, you take all the sets which does not contain infinity. Okay. That has to cover.
X is a metric space.
Hmm.
Then can you always make X bar a metric space?
That's what I'm going to come. That's what I was discussing before this. Some Hilbert cube and other things. No. I mean, it can, if it is locally compact and separable, then we can do that. Separable, yeah. So, if and only if it is separable. Okay. If and only if it's clear, because if X bar is metrizable, if it's a metric space, then it is, I mean, it is compact. Okay, if it is compact, then it has to be separable. Then the subset also has to be separable. Okay, because of that. So it is if and only if it's separable. But I am not going to prove it. I think you will see the proof in the next course. So I am not proving it. Okay? But I will be using that fact. Okay? I'm going to use this to prove Stone-Weistrass theorem for locally compact. Okay? I'm not going to discuss locally compactness that much. Okay? Only this. So it's compact. Is that clear? If it it's clear, no? Why is it clear? If one of them, infinity is in one of them, so then its complement will be compact. So yeah, that will have a finite subcover. What will have a finite subcover? I didn't understand.
Infinity should be there in one of these.
One of these, right?
Take just one of them.
Yeah.
Its complement
Yeah.
is
Compact.
and will have finite subcover.
Yeah.
So there will be some n different, let's say u sub
Yeah,
alpha.
and yeah.
They will cover that.
Then,
total union will be.
okay, yeah, correct. That's all. You need one. You need one of them. Yeah, that's right. I was wondering about the other one. Yeah, if infinity is in one u alpha naught, okay, then the complement of u alpha naught, okay, that can be covered by finitely many of them, which should be covered by other things, finitely many of them. Then you take, this is also one of them. So union, this should be X bar. That's all. Okay. I leave it as an exercise. It's clear. Okay. Yeah. Okay. So, okay, this is examples of that. Then we want to consider the following. So this is a fact, okay, which I am not proving. Okay, X is locally compact and separable. By locally compact, we mean it's a metric space. Okay, metric space separable. Then X bar is metrizable. That means whatever the topology we have defined, X bar with this tau tilde, okay, is metrizable. That is, whatever the topology we have defined, it comes from a metric. We have in the assignment, there is one problem. You have this, I mean, this is something called 2-point compactification. You can add 1 point or you can add 2 points. Okay, minus infinity. We have defined a metric on this. It will be an equivalent metric. It's not the same metric as an R. You have it's an equivalent metric. I mean, if you have the same metric, then it will take from infinity to any point, the distance will be infinite. So we don't consider that. Okay, but we have a different, by using, you can make this minus infinity. You can make this isomorphic to minus 1, 1, that open interval. Then you can define a new metric on that. Okay, So that's what done in the assignment. So similarly, I mean, in fact, if you have R2, if you add one single infinity to that, that will be a sphere, that will look like a sphere in R3. And I mean, it's always the case. If you have Rn, if you add an infinity to that, that will be a sphere in Rn plus 1. You can show that that is isomorphic to that and homeomorphic to that. Okay? And so you have a metric always there. You can see that there is a metric. And incidentally, one more thing I forgot to say, which is easy remark. In a non-linear space, locally compact is equivalent to saying all open balls are compact. If I mean the locally compact says that there is one open ball which is compact, then all the other ball you can have it as a continuous image of that, right? You can shift it and continuous image of that. So every ball is compact. In a non-linear space, there is one ball which is compact. Then the other ball you can just dilate it and translate it, and you can get to any other ball, which are a continuous operation. So continuous image of compact set is compact, so they are all compact. Okay? So non-linear space, all is locally compact is equivalent to saying all balls are compact. But other in metric space, it's something else. I mean, in metric space or in topological space, you have to do the all of them need not be there. But if there is something, then there is something inside. There are many things in the metric space. I don't want to go through all that, so that's why I mean it will take one class. So I'm not doing that. Okay, so you will do it in the topology case. We will stick to our analysis, not topology. Okay, so okay. X is we are considering metric space. I mean, we are dealing only with metric space. For us, the X bar is also a metric space. This is true even in topological case, correct. Locally compact topological space, it's true. If it is, I mean, second countable, locally compact, maybe as he says, there is some Hausdorff normal, I'm not sure. Normal may follow. I don't know what follows, what do. I have to check. Normal and second countable, okay. Normal and second countable, I have to look at it. So under some condition, the separability is one of the conditions. Separability you can't avoid because if X bar is metrizable, okay, then separability, if it is, I mean, if it is compact, if it is metrizable, then it is separable. So subspace should also be separable. Okay, that you can't avoid. Okay, so if we have time, we will do it. Okay, we will try to do. It's not. It will take one class. If you have time, we will do it. Okay, so then we want to consider the following. So for the time being, for our class, we assume that our X bar is also a metric space. Why I need is a metric space? You don't need it to be a metric space because the last class Bhanugaran proved only for a metric space. Stone-Weistrass theorem for a metric space. Okay, metric space is used there, so that is why I need that. Okay, I mean Stone-Weistrass theorem is proved for C of X where X is a metric space. So I need it to be a metric. But Stone-Weistrass theorem is true if X is compact Hausdorff. Okay. Now, so X is locally compact. Okay. We define C0x. Okay. This is what is called as continuous function vanishing at infinity. There is no infinity here. Infinity is only you add it later. This is the definition. Okay. Continuous functions vanishing at infinity. Which is by definition, this is the meaning of that. By definition, all those f in C of x continuous function, okay, C of x means continuous function, such that for all epsilon, for given epsilon greater than 0, for epsilon greater than 0, there exists a k compact such that f of t is less than epsilon for all t in k complement. Okay. Outside a compact set, it's less than epsilon. Mod of this is less than, of course, it's a complex valued function or real valued function. For this definition doesn't matter, but when we prove Stone-Weistrass theorem, we will consider real valued function first. And by the same trick which was used, it will be true, I mean, under one more condition. The conjugate is also there, one more condition, it will be true for complex valued functions also. So I will come to that later. So this is the definition. Okay. This is the right non-linear space when you have locally compact. When it is compact, when the x is compact, then C of x, all continuous functions, there you can define a norm because they are all bounded functions. But in general, if you have a locally compact, then continuous function need not be bounded. If it is not bounded, you can't take the supremum and you can't define the norm. To define the norm, we do this. So outside a compact set, it vanishes. It's like this. It's less than epsilon. It goes to 0 as it goes to infinity. That's what vanishing at infinity means. There is no infinity in the, there is no infinity here, which we will add later in the compactification. But this is what it means. Okay. So this is an exercise, very easy. I can tell you. Okay. Assignment. Small assignment. Okay. C0x is a complete norm-linear space. I will tell you what is the norm. Complete norm-linear space with respect to norm of f infinity. You have to prove that it is bounded, which is clear. It is continuous and a compact set, so it is bounded there. And outside it's less than epsilon, so it will be bounded. So its boundedness is clear. Okay, norm f infinity is equal to supremum of t in x mod f of t. Okay, with respect to this. Okay, this is an assignment. It's very easy. Same thing. These are all bounded, so it's contained in bounded functions. So which we have proved it's complete. Okay, so it's clearly you can prove norm is very easy. There is nothing. So to prove that it's complete, you have to prove that it's closed. That's all. Okay, it's the same as that. Only you have to prove that the limit also vanishes at infinity. For that you need little bit work. There is nothing. Okay, since it's slightly non-trivial, I'm giving the assignment. It's not very trivial. Okay, okay. So this is a complete metric space. Okay, then we have to prove the following theorem. Okay, A contained in. So this is a C0x is a vector space. It has a norm, so it is a norm linear space. Okay, and it's also an algebra. Algebra means it's a ring. It's a vector space as well as a ring. It's also a ring. You can multiply pointwise any two things. So it's an algebra. So you have a subalgebra. Okay, you have a subalgebra such that A does not vanish. Such that A separates points. Same definition. If you take 2 points x and y, then there is a function in A separates points. Function in A such that f of x is not equal to f of y. The same definition, okay, which is used for that. Okay. So this is the definition of separates point. Okay, and A does not vanish. I'll tell you what it means. This is the definition. That is meaning of not vanishing in that. Okay, for any x, there exists an f in A such that f of x is not equal to 0. Okay, that's all. That's what it means by it does not vanish. So there is no point where all functions are 0. Okay. Then A is these are the conditions. No, it separates point, does not vanish. This is equivalent to saying it contains constant. Okay, then A is dense in C0x. Okay. One is function 1 is not there. It doesn't vanish, no? It's not there. Correct. Constants are there. Okay. That's for compact, not for this. For compact, yeah. I'll come. I'm going to prove it because we are going to use a version in European different Stone-Weistrass theorem. So I will prove that and come to. Yeah, you're right.
epsilon by x.
Exactly. For every epsilon, that's what it vanishing means. So it convert. There is no infinity in that. Suppose there is an infinity. In real line, there is no infinity, right? Real line, there is no infinity. But you say talk about x going to infinity, something goes to 0. So when something goes to infinity, it goes to 0. That's what it means. Okay. Okay. So we'll prove this. This is the Stone-Weistrass theorem for locally compact metric space. So we will come. So here we are assuming X is locally compact. It's a metric space. Okay. Okay. So to prove that, we have the following proposition, maybe theorem. What are all the things I need? Yeah, theorem. This is also Stone-Weistrass theorem. Okay. X is compact. Okay. And A contained in C of X separates points in X and does not vanish in X. That's all, no? It's an algebra, of course. It's an algebra. That's very important. Then A is dense. We'll prove this first. All we have to prove is A closure contains constant, right? I mean, in the proof, if you look at the proof, it is used that A contains constant. But actually, if you do, I mean, the proposition, it's used that A contains constant. But if you look at the proof, it is enough if A closure contains constant. You want to prove A closure is everything, okay? And you need constant to produce some function. If it is, it's enough if it is in the closure, okay? So that's what we need to show. So proof of this proposition, this is another version of Stone-Weistrass theorem. Instead of containing constant, we have another condition. It does not vanish on that. So we have to prove that does not vanish. Of course, if it contains constant function does not vanish anywhere, provided constant is not 0. So we have that condition. So we want to prove that this is equivalent to that. So we want to prove if this is true, then it contains constant. Okay. Okay. Yeah. We know enough to prove. Only we need to prove constants are in A closure. Constant functions. Okay. One is in A closure. The function 1 is in A closure. Okay. The function, constant function 1 is in A closure. That's what we want to prove, right? Okay. How do we prove that? So we have the condition is it does not vanish at any point. A does not vanish. All function does not vanish on one point. So for any given x, for any arbitrary x, there exists an f which depends on x such that fx in C of in A such that fx at x is not equal to 0. Okay. Then you can multiply, I mean, fx is not equal to 0, then you can multiply and you assume that fx is equal to 1 by constant. It's an algebra, so you can multiply by that. You are not adding a constant. There are no constant. You are not adding a constant, only multiplying by a constant, which is okay. Okay, fx equal to x. Okay. Okay. Same idea. Now define ux equal to all those y in x such that y in x such that fxy is greater than 1 minus epsilon. Okay. X is in ux. Okay. So this implies union of ux equal to x. So there exists, since x is compact, there exists x1 up to xn such that x is equal to union of uxi. Okay. That is there uxi means there exists in fxi for x fxi. Okay. Let f is equal to maximum of f x1 up to fxn. Finitely many. Okay. If you look at the proof, the Stone-Weistrass theorem, earlier proof, how do you prove that maximum is there? You take polynomials in C01, polynomials or polynomials in 0, 1, okay, and that this Pn converges to square root function, okay, t going to square root t, okay. Then this Pn of f square by norm f infinity square. Okay, these are all there. This will converge to mod f. Then once you have mod f plus g plus or minus f minus g, that will give the maximum. So it's there. Okay. So this is the key. In that, if you look at those pn's, pn of 0 is 0. If you look at the definition, so constants are not there. Okay. Look at the proof such that pn 0 equal to 0. Okay. That if you look at the proof, P0 is 0, P1 is defined by some PNT something, so P10 will also be 0. Recursively it is defined, inductively it is defined, and you can see that all those Pn zeros are 0, constants are not there. And polynomial times any function is there because it is an algebra. Sum of what? Why am I taking sum of fxi? So yeah, I can take that, but we want to get a constant. So I want to do something. You can take anything you want. I'm just giving this example. But why do you want to take? What you will do? I'm sure. I think that may also work. But for what I'm doing, but I just want to produce constant there. Number 1 there. Constant function 1 there. This is not constant. I didn't say this is constant. I'm going to get constant from this. So he's asking how will you get constant? That's all. So by taking some of them, how will you may get it, but how do you get it? I'm not taking because I have one proof like this. That's all. There's no other reason. You can take another anything you want. Okay. I am just saying that because this is maximum, you can take maximum in. I mean, this is the following theorem. If A contained in C of X, okay, if it's subalgebra, we don't need constant. Okay, then it is a lattice. Lattice means maximum and minimum are there. Okay, then it is a lattice. You don't need it to be separate points, or you don't need it to be contain constant. Huh? Closed. Okay. Yeah, closed. Yeah, then it is a lattice. Lattice means maximum and minimum are there. Maximum of two function, minimum of, you can take maximum or minimum. Okay. So I am just using that. Because of that, then f is in a closure. Okay. All I am saying is f is in a closure. Now I want to define a function. So f is in a closure, and we know that f is maximum of that. So f of t, mod f of t is greater than or equal to 1 minus epsilon, right? It's greater than, at least this is what I want. Okay, some number m greater than 0. That's what I want. Now you just define g from there. So from 0 to norm f is fixed now. Okay, norm f infinity to r by f of g of 0 is 0, and g restricted to this m to f infinity is just 1. You can take a straight line if you want. From 0, from m to f infinity, 0, then you have m to f infinity. Okay, this is number, of course. Here it is 1, here it is 0, here you can join by a straight line. Okay, you have a continuous function like that. Okay, that's fine. You take a g like that, then g is continuous. Okay. Epsilon I have swallowed. There is no more epsilon. All I want is, I want f is greater than 0. There exists a function such that its minimum. Okay. I don't even need this. All I want this. Sorry, I want this. No more. I mean, I have taken epsilon and other things. Just like some epsilon. Okay. Then I don't need the epsilon. I'm just saying f of t is greater than this. That's all. Okay. Now I define a function which is 0, which is 1 between m to f infinity, supremum of that, which is just a line. You can take the straight line. Okay. No, it is 0 at 0. Now, if it is, then it will not be continuous, no? If it is 0 everywhere. Okay. So G of 0, G is in C of X, and G of 0 is 0. Sorry, G is in 0, 0 norm F infinity. G is in 0 of 0 norm F infinity. Okay. In this interval. Okay. And G of 0 is 0. So there exist polynomials. One second, let me just write it. F infinity such that n of 0 is 0. No constants are there. There is no constant terms such that Pn converges to G uniformly. Okay. Now, what is the problem? P here. Here. This is the earlier proof I recalled. This P. Here. P is polynomials. Okay, polynomials. For here it's polynomial. Initially I wrote C, I have to write no polynomial, so I just wrote it. Sorry, P is polynomial. Here also it is polynomial, not power set. P is polynomial. Okay, you use a different P. Okay, yeah. So now there are. I mean, this is continuous function by the earlier proved version or Weierstrass theorem, original Weierstrass theorem. There is this polynomial which goes to this. And you can take P and C is 0. There exists polynomial which converts to G, but then if you take then you can subtract P and 0 from that. If P n has a constant term, subtract that P and 0. P and 0 has to go to 0 because G of 0 is 0. Uniform convergence will imply point-wise convergence. So P and 0 should contain to C 0. Okay. So there exists, so you can subtract that. Okay. So there exists polynomials without constant term converging to this. Okay. Now Pn of that F will converge to G of F. Okay. But then G of F is 1 because F takes values from M to norm F infinity, where it is 1. That's all. It's okay. Anyway, look at it. I haven't done anything. I use the fact that it doesn't vanish. Then I took a function which is 1 between. I mean, use the fact that it doesn't vanish. Using that, I produced a function which is strictly greater than 0, which infimum is strictly greater than 0. Okay. Then for that function, I took this M and F infinity, and I have a continuous function which is 1 here. So if you compose with that function, I should get there. But then that may not be in that. So I took polynomials which converge to this without constant terms, and using all those things I got it. Okay, just be careful and look at it. It's just okay. So now we have proved that theorem. So what is remaining is the fact I have written already. Okay. So X bar is also a metrizable space. Okay. Stone-Weistrass theorem holds there. C0 say X is locally compact. There is one more theorem. Sorry. This is also a version of Stone-Weistrass theorem. After this will come. So theorem. This is another version of Stone-Weistrass theorem. X is compact. Okay. A contained in C of X. Algebra, of course. We deal with algebra only, which separates points in X. I am not using, I mean, there may not be any constant. There is no condition of constant or not vanishing. Those conditions are not there. Then either A closure equal to C of X or A closure equal to there exists X naught in X such that F of X naught equal to 0. Okay, there is some point. Remove what? Sorry. Set of all F in C of X Okay, a closure equal to, okay, let me write this way, a closure equal to a x naught for some x naught in x, where this is equal to all those f in c of x such that f of x naught equal to 0. First notice that this is closed. Okay, if f all those fn vanishes at x naught, then the limit will also vanish, so it's closed. Okay, so this is the closed subset of that. It's complete. Huh? How? I'm going to prove it. This is theorem. Theorem says that Stone-Weistrass theorem, that if something has constants or if it does not vanish, either of those two conditions are satisfied, both are equivalent, that's what we have proved, then the closure is everything. So without having that condition, constants are not there, then it cannot exist. Okay, constant function does not vanish anywhere. So there will not exist a function in A, there will not exist a function such that, I mean, not in A. I mean, it will not all of them. There will exist function. What I mean is, there will exist at least one function such that this doesn't happen. Okay, here it is equal to all those functions where this happens. Okay, if it is constant, it cannot be the case. Okay? So when constants are not there, then this is the case. That's what I want to say. There exists a x naught such that this happens. Since it separates point, there cannot exist 2 points where they are 0. It's not possible. There exists only one point like this. Okay, this is an ideal in that. If you look at it, it's a maximal ideal. Correct. Yeah. Here, g of f is defined to be 1 on m to f infinity. F takes values. F is greater than m. F takes values from here to here. F is always less than normal infinity. F is greater than m is what we have taken. That's all. When you compose g of f, f lands up here where g is 1, so it is to be 1. That's all. Okay, so we want to prove this version of Stone-Weistrass theorem, which says that if you don't have the condition, if you have only separates point, then that is this. Okay. I don't know why it became late. Okay, proof. Of course, if constants, if 1 is there in A closure, then Stone-Weistrass theorem says that A closure equal to C of x. So assume 1 is not in A. Okay. Then we have to prove that we have to produce an x naught such that this happens. Okay. Okay. How do we get an x naught here? Yeah, no. So we have already proved that if it does not vanish at all the point, then it has to contain constant. We have already proved. So there exists one point. Okay. Since constants are not there, since 1 is not there, there exists x naught. I mean, if it does not exist, then constant has to be there. That's what we have proved. Okay. I mean, we have already proved that if it does not contain, if it contains constant, then it cannot vanish. Okay, so if I mean, then yeah, if it is equivalent to saying it does not vanish, it is equivalent to that. Okay, so if it does not contain constant, it has to vanish somewhere. Okay, that's what we have proved. Okay? If it contains constant, if it contains 1, of course it cannot vanish. If it does not vanish, it contains constant. Both direction we have proved. Okay, so there exists the x naught in x such that f of x naught equals 0 for all f in G, and in particular a closure also. Okay, I mean, if it is true for A, then it's true for A closure also. Okay. Okay. Now we have to prove that okay. I mean, for all this A it happens, right? There exists a single X naught. We want to prove that. So the claim is this: if G is in A closure, then there exists a Fn. Okay. No, we proved it for A closure. No, constants are not there in A closure. Now, if it is in A closure also, it's true. If at one point all the functions in A vanishes, A closure functions also vanish because it's closed. Okay. Okay. Now the claim is we want to prove A closure equal to all those F such that F in C of X such that F of X naught equal to 0. We want to prove the other way. We have proved that A closure is contained in that, but we want to prove it is equal to that. Okay. To prove it is equal to that, if you have any function which satisfies this, then there is a sequence in A which sequence in A or sequence in A closure doesn't matter. Okay. You can approximate by A closure also. Okay. A closure which converges to that. Okay. So this A closure does not contain constant. So let us add that. Let A tilde equal to A direct sum. You just add that. Okay. Which is just F times C1. Okay. I mean, here we are considering only real functions. I'm sorry, I should have said it. The C is continuous functions taking values in real. For complex, you have to do separately. The same thing, same trick will work. Okay. I just take it like this. This is an algebra, you can see. This is just the direct sum of A with the complex number. I'm sorry, real numbers. You are just adding one more dimension. A tilde like that, which is an algebra. If you take multiply something F plus C1 times G plus C F2 plus C2 1. Okay. Then if you multiply F1, F2, then it's clear, right? So because it's an algebra, it will look like that, and that is also an algebra. Okay. So A tilde contained in C of X algebra. Since A separates points, this is a bigger one, so this will separate point. This contains constant. Okay. So this implies Stone-Weistrass theorem implies A tilde closure is equal to C of X. Okay. Now, suppose G is in C of X such that G of X naught equals 0. Okay. Then there exists Fn plus Cn, okay, which converges to G uniformly, of course, in norm infinity. Okay, by this. What is F? F is in A. Yeah. I'm just taking A direct sum R as a vector space. Okay, that's all. C is constant. This from A, I'm defining A tilde. You take F is in A, you take new tilde F plus C, that's all. If polynomial is there, then add the constant term, that's all. Okay. Then Fn plus Cn converges to this. Okay. G is in, suppose some G is there such that G of X not equal to this. Then there exists, because I mean, by earlier Stone-Weistrass theorem, this closure is this. Because of that, there exists an Fn plus Cn converges to this. Okay. This in particular, this is uniform convergence. At 0, this converges. So in particular, Fn 0 is 0 and G of 0 is 0. Sorry, Fn x naught is, I mean, Fn x naught plus Cn converges to G of x naught. But these two are 0. This implies Cn converges to 0 as constant. Okay. Norm of constant function is Cn itself. Okay. Now it is clear that now you just have to verify that Fn minus G norm, or maybe Fn minus G before norm, let us take some t. Mod of t is less than or equal to Fn plus C at t minus g of t plus Cn plus Cn mod Cn. Okay, with this goes to 0 and this is less than or equal to this. These things imply that this norm infinity supremum of that goes to 0. Yeah, well, I will write there. F of t minus g of t is less than or equal to f of t plus c minus g of t plus mod c. This goes to 0. So this implies, sorry, f and t, sorry, f and no, yeah, f and t, f and t. This implies f1 converges to z norm. Okay. I mean, this is true for all t. Okay. You can make this less than epsilon or something. So this will be less than this and usual. Okay. So we have proved that Stone-Weistrass theorem. Next, this is a remark, proof, assignment, or let me see what it is. Okay, let me see. Okay, this is the statement is the okay proposition. Let's see what it involves. Okay, there exists a phi from C0, X is locally compact. X is locally compact. Then there exists a phi from C0x, this is a normed linear space with respect to the sup norm, okay, to C of x bar. This is a one-point compactification. And let's assume that that's also a metric space where this is embedded, but the x sits inside as an open set topologically. I mean, that whatever the metrizable metric we get here need not be the same metric here. It is just a metric space. So that the Stone-Weistrass theorem is true, that's all. Okay. But density, all those things are topological facts you are talking about. Okay, so it's okay. Okay, so there exists a phi which is an isometric isomorphism. What it means by isomorphism? By isomorphism, I mean, whenever you have two objects, you say something is an isomorphism if it preserves everything. Okay, what are all the structure here? Here, this is an algebra, this is a vector space. So this is a vector space. So phi has to be linear. Okay, so this is linear. Of course, they are sets, of course. So isomorphism means it should be a bijection first of all. Bijection. Okay, it should be a bijection. It's linear. It's 1 on 2, and it is also an algebra. That's why it's an algebra. So it has to be a homomorphism. Okay, that's what isomorphism means. Isomorphism means it's a linear homomorphism. That is an linear bijective homomorphism is an isomorphism, and it's an isometric. I said there is one more structure which is the norm. So it preserves the norm such that norm of phi of f infinity, both are infinity now, is same as infinity, f infinity. Okay. Phi of f will land here, that will have a norm. That norm is same as this. This is the norm linear space. Even when x bar is just a topological space, compact T2, this is a norm linear space. Okay. There is no, this is a metric space, nice metric space, norm linear space. We are using the fact that it is metrizable only for the proof of Stone-Weistrass theorem. We have proved only for a metric space, so that's why we are using it. Okay. Otherwise, I mean, you can take to be just compact T2. T2 means Hausdorff. Okay. So this is a statement. I thought I will finish these things in half an hour, and I wanted to give you a quiz, but it already took a lot of time. Somehow I took a lot of time. I don't know. I thought I will finish it in half an hour. Okay. Shall we do after the class? But don't send message to me. No. Eh? You have a tutorial. Okay. Okay. So I will do some other time. Okay. So yeah, someone was asking for it, and that person is not here now today. Yeah. He has gone home for Diwali, I think. He was saying precisely because people will go for Diwali, so we better give it now. And he is not here. No, no, no. He wanted to be in Diwali time. Not in Diwali. Oh, okay. Okay. So his request is okay. Okay, then I can go through this. This is easy. So if we have a f in C of x, okay, f in C0x, okay, it's clear how you are going to define. Then define P of f, which has to be a function in x bar. P of f acting on t is just f of t if t is in x, and P of f at infinity is 0. That's all. Okay. Or if you want, you can call it P of f to be f tilde and do this. Okay. That's okay. Then everything will satisfy, right? All this function f of infinity is 0. So it is linear, that's clear. If you have a lambda, you can take it lambda, sum is sum, and it is 1, 1 on 2. If you have any function which is like no, sorry, there's something wrong in that. Sorry, this is C of x. This is all those functions C of x vanish at infinity again. It's not C of x. Sorry, this is just then going to all those f in C of x bar. I mean, this is compact. This is all such that f of infinity is 0. I mean, to use that only we proved that theorem. Okay. Correct? Right. Okay. If you have any such function such that f of infinity is 0, it is continuous. Okay. So this need this ontoness needs some work, little bit of work, right? I mean, so I have defined it like that. Then you know that it's linear is clear, and its homomorphism is clear. Fg will be the product again because at infinity both are 0, so it will be like that. And its 1, 1 is clear. Okay, because at infinity is 0, so it has to be, it's clear, it is 0 everywhere, it has to be 0 there. I mean, for you to check for linear map to check 1, 1ness, it is enough to see that t of x equal to 0, x equal to 0. Okay, that's what, so that you can check. Okay, ontoness you have to check. Onto means if you have any function such that f of infinity is 0, okay, since it is continuous at infinity, it has to vanish at infinity. I mean, it has to vanish at infinity means that epsilon condition. Right? Since it is continuous, yeah, it is continuous, yeah, because of that. That is precisely the topology. If you want, you don't have a matrix, okay. The point is this, you want to use the continuity with respect to topological definition. F inverse, topological definition is F inverse of open set is open. Okay. So maybe I will give this assignment. Okay. Just this. Just onto, I mean, other things you can just write. It's clear. It's on all these things. Continuity on to only you have to check. Okay. There are 2 assignments in this class. Please note it. This is assignment 2 of this class. Okay. You have to check it is on to. So to prove on to, you take a function in C of x, say this here, at infinity is 0. At infinity means 0 means when you restrict that function to x, you get a function in x. That function has to vanish at infinity. Vanish at infinity means given epsilon, there has to be a compact set. Outside that compact set, it should be less than this. That follows because of this topology. You have to use the fact that continuous function, I mean, you have to you take this, then I'm going to prove. You take the inverse image of minus epsilon epsilon. Okay. So the complement of that will be compact here. Okay. So it's easy. Okay. I mean, just so that you have understood. Okay. So just like that. So this is assignment 2. And from this, it follows the Stone-Weistrass theorem follows, right? Stone-Weistrass theorem. So this is the theorem. Where is the theorem? I have erased it. X is locally compact. X is locally compact. Okay. Then A contained in C of x is separate points in x does not vanish. Then A is dense. A closure is C of X. Okay. Using this definition, you take A as A bar in A tilde in this P of A. I mean, this proof is also, I don't want to leave, I don't want you to write this. Yeah, let's just write it. You only have to prove that, you know that proof. You know that C of X is isomorphic, isometrically isomorphic, okay, to all those F in C of X bar such that F of infinity is 0. Okay. Using this phi. Yeah, any question? No question. Okay. Then phi of this A, okay, it does not vanish anywhere in X, it vanishes only here, only at infinity. Okay. So F of A is contained in this C of whatever here, okay, which satisfies all the other conditions. It separates points. It separates infinity. I mean, it does not vanish anywhere. So it separates infinity and any point there. Okay, there exists a given any point, there is a function which is not 0 there. So if F is in say F is in this, F is here. Sorry, if X is in X bar, if XY in X bar, if XY is in X, okay, then there is a F in A such that F of X is not equal to F of Y. Okay. If X is in X and infinity is in X bar, okay, there exists a F in A such that F at X is not equal to 0 because does not vanish is one of the conditions. Okay, and this and F of infinity is 0. So it separates points. Okay, whatever phi of F at infinity. Okay, phi of F is same as phi of F. Okay. Say it again. Yeah, C naught of X is correct. I didn't say that, I forgot. Yeah, this is for C naught. Sorry, A is in C naught X. There is no C of X is not a nonlinear space. Okay. Only I mean, C of X is for a general, I mean, they are not bounded, right? So only for A containing in C0X, we talk about this. Hmm? Yeah. Let's say it again. There is no, what is alternate proof? What is the theorem? We didn't prove this. We proved for compactness, compact set. We didn't prove for, I just stated it for locally compact. Now only I'm giving the proof. After all this thing, I stated compact. Then I proved a different version for C of X. Then this version, which says that for you don't, then you get this version. These things you will get this. Yeah. Okay. Where was I writing? Yes. Okay. Here, no? Yeah. So, yeah, we have this isomorphism between this. So it's enough to prove that, yeah, this will be C0. Correct. Yeah, C0. When I said vanish at infinity and all this, I said, yeah, I just didn't write C0. It is C0. Yeah. Did I make this mistake anywhere else? No. Now we use that. So now C0X, we embed it here, okay, in this. Okay. There it satisfies the following condition. There this A satisfies under this embedding, A separates points in X bar also because it does not vanish in X. Okay, so it separates any point in X and infinity. I mean, it separates any 2 points in X. It separates infinity and X because it does not vanish anywhere in X. Okay, so because of that, because of this condition, it separates infinity and X. Okay, so because of this, from that version of Stone-Weistrass theorem, okay, this phi of A has to be all those functions F in such that F of infinity is 0. That's what precisely we want. If you have a question, taken more time. Yeah, any question? You have to go over this. Okay. Okay. Yeah, yeah. This is just we are using. So this is what has happened. Last class, Banu Kiran proved Stone-Weistrass theorem, assuming three conditions. Two conditions or three conditions. Separates points. It's an algebra. Separates point containing constant. Then we proved here that containing constant is same as saying that it does not vanish. Okay, I mean all functions in A does not vanish. Then we proved another version here, which is that you remove that constant condition, containing constant or not vanishing that condition. Then either it has to be everything. If it contains constant, it will be everything. Otherwise, there will exist a point. There cannot exist two points because it separates things. There will exist a one single point where all functions vanish. Okay, so we take that version. Okay, now this is the theorem for locally compact. Sorry, where is the theorem? This is the theorem for locally compact. Okay, something is in C0x. There are two conditions. It's an algebra, of course. It's an algebra. I wrote it here. I mean, the earlier theorem I have written it. It's an algebra, and there is no constant cannot be there because it all functions vanishing at limit. Constant cannot be there. So it's an algebra. It does not vanish at x. Okay, does not vanish on x. These are the two conditions: separates points and this. So then we want to prove that this closure is everything. To prove that this is C0x is nothing but under this isomorphism between functions vanishing at infinity and all functions. Here also function vanishing at infinity only. Okay, but this is function on x bar. This is function on x. Okay, under this condition, these two are same. So I mean they are just isometrically isomorphic. This is just you are taking it here. That's all. The same thing, same space. It is what is called an embedding. It's an isomorphism. I mean, it's not an embedding. Under a big C of x, it's embedded. Okay. Then use that Stone-Weistrass theorem. That another version we have proved. There exists. I mean, without by relaxing the second condition, constants are not there. So use that version. You get precisely what you want. Verify the condition. You get precisely what you want. It's all direct verification. Okay. That's all. Here. Okay, you have, so I have this is a theorem. Okay, A is something which is an algebra, it separates points, that's the only condition. Then either A closure is everything or there is a x naught such that this happens. If it contains constant, then everything, it's everything. If it doesn't contain constant, then it cannot, it has to vanish at some point. If it doesn't vanish, then it contains constant, we have proved. Okay, so it has to vanish at point. So there is a point where it vanishes. There is only one point where is it vanish. It cannot vanish at 2 points. Okay, so there is, because it separates points. There is one point where it vanishes. Okay, now you take that point. Now I add constant to that. To that A, I add constant. Okay, now it contains constant. It separates points. So its closure has to be everything. Now if you take any function here, that will be approximated by some function fn plus cn, and cn's are useless, is that's what I'm saying. Cn goes to 0, so you can just remove it. I mean by the theorem there is some fn plus cn, but cn has to go to 0 because at x naught it is 0, so cn has to go to 0. So you can subtract cn, still that will go to g. That's all. There is nothing in this. We have already used this kind of trick for polynomials and other things by removing the constant term and other things. Okay? That's all.